Okay, let's begin. So you can make a little correction in your notes. Last time we actually did 1.3. I know I labeled it as 1.1, but I kind of don't always follow the textbook because I find that the narrative works better if I teach things in a different order. So I started with 1.3, then I go to 1.1 and 1.2. Then I told you a little bit from 1.4, and I'll go back, then I'll go to chapter 2 and come back to chapter 1. Because I think it makes more sense to talk about things in a certain order. And because I finished teaching this class the last time, like the day before I started teaching this new section, I didn't have time to rewrite a lot of things. So if I had my way, I'd actually teach chapter 8 and chapter 4 intertwined as well, but whatever, we'll do them separate. Because they go basically over the same thing, just a different context. I don't think there was a need to separate them. So yeah, we know about matrices, matrix operations now. So we know what matrices are in the trivial sense of the word. Chapter 4 and 8 is what starts to introduce this idea of them being linear transformations. But so far we wouldn't really know that. So we kind of know how to add to matrices, multiply to matrices, what they are, different kinds of matrices. And now we're going to actually look at one of the most basic applications. So this is 1.1 is what we're going to do today. And this is called a system of equations. So we're going to look at systems of equations. Okay, so let's start with the definition. System of equations, and we can write for emphasis linear equations. This is linear algebra, or you can say a linear system of equations or a system of linear equations is a set of equations of the form So we can have a bunch of equations in this order where x1 to xn are variables or unknowns. And a11 all the way up to amn are constants. Scalars. The size of the equation is given by the number of rows and the number of columns. You'll notice here that this has m rows and n columns. Right? If I look at, ignore all the plus signs and sort of look at these as just an array. If we have n variables and n equations, we call this an n by n system. Or this is pretty much equivalent to simultaneous equations that you would have seen in algebra class and pre-calc class. Right, so every now and then you have a situation that you can model by taking a bunch of linear equations considered together. Usually you did with 2 or 3 variables, but now we want to get a lot more general. We can do it with up to n variables. And if we have all these guys, and this form is important, notice that none of the x's are raised to powers other than 1 and etc. Right? Your a's have to be constants. Your b's are also constants. The b, i's, also constant. So we can have an example. So x plus y equals 3, x minus y equals 1 is a 2 by 2 system. Or you can have 3x1 minus 7x2 plus 2x3 equals 9, and x1 plus 3x3 equals 7 is a 2 by 3 system. The solution to an m by m system is an n by 1 column vector. Such that all equations hold for these values of x1 to xn. Right? So find me a list of values for the variables x1 through xn such that if I use those values, literally every single equation in this system will make sense. If no such vector exists, then the system is said to not have a solution, and we call that inconsistent. By the way, a system that has some solution is called consistent. Right, so we'll talk about consistent and inconsistent systems later, but I'll just throw those words out now. So system of equations is just a bunch of linear equations that you consider together. Solving the system of equations, finding the solution to a system of equations, you are just finding a vector that if your x values take on, if your variables take on those values, it will literally solve all equations in that system. If no such vector exists, the system does not have a solution, and you call it inconsistent. So let's actually bring this to linear algebra now then. Note. By matrix multiplication, we may write the system. I mean, I erased it, but you can look back in your notes as, notice that I could do this manipulation and write it in terms of matrices. A11, A12, all the way down to A1n, A21, A22, all the way down to A2n, A1, A2, all the way down to A1n. X1, X2, all the way down to Xn. That's my B1, B2, all the way down to Bn. Right? Notice that that is true. Based on what we have defined for matrix multiplication, take this times that, you get the first equation. Take this times that, you get the second equation, and so on. You can actually repopulate the entire equation by doing this, right? Because these guys would be equal to, just imagine, pretend what brought over here, there's a whole matrix around this guy and a whole matrix around that guy, and the corresponding equations are equal. So we can actually express the system in terms of matrices. And there are standard variables that we use to represent these. This guy is called A, this guy is often called X, and this guy is often called B. And so we describe this system as AX equals B. So this is just a generic representation of a system of equations. And now matrices are in the game. And that works by our definition of matrix multiplication. So that's very nice how it works out. A has a name here. It's called the coefficient matrix. You'll notice that it is the matrix of coefficients, right? It's all the constants that we're multiplying all the x values. They all end up here in their relative positions when we wrote things in that order. X is called the solution matrix because the solution is finding the vector here that will solve the system. And B is called the constant matrix. So you have a system like this, and that's your coefficient matrix, that's your solution matrix, that's the constant. To solve the system, you need to find this guy that makes it work, make everyone work nicely. The form AX equals B is called the matrix form. Of the system. We can actually get a little bit more efficient here. And just as how I did in lecture 1 where I was showing you how to think of functions as matrices, I can somehow ignore the variables because I would know in my head what they are. So writing them down is sometimes just not necessary, it's very superfluous. So I can kind of ignore them and it's understood that they're there. And so we can get another form. We can write AX equals B as just one big matrix where I put the A values here and I would write a bar and put the B values here. Or if you like writing matrices with the square brackets, you can write that. I.e. as you can write one huge matrix and write A11, A12, all the way down to A1n, A21, A22, all the way down to A2n, AM1, AM2, all the way down to AMN. There's B1, B2, all the way down to Bn. And I can write it that way. This is called, whenever you do this, this is called the augmented form. And by writing it that way, you say you've augmented the system. So we can have a system of equations. We can write it the same way we did in algebra class all those years back. Or we can throw matrices in the mix and write it in the form AX equals B, which is called the matrix form. Or if it's superfluous for us to write down our variables, we can write it in this form, which is called the augmented form. It is understood that the first column of guys correspond to the coefficients of the variable x1. The second column corresponds to the coefficients of the variable x2, and so forth. The last column corresponds to the coefficients of the variable xn, and that's sort of understood. Whenever the names of our variables are understood, we don't have to write them. Right? And this is going to be a nice form that we're going to be able to take advantage of. And odds are, if you enter a system of equations into a computer, it converts it into this form in order to do whatever you want to ask it to do. It's going to be a very form for algorithmic purposes. And we say we've augmented the system and we write it that way. Let's make sure we actually know how to do that. So let's just do an example so far. What's wrong with this? So this is just definitions. This is just how we can write things down, and I want you to know the names that I call everything. So if I say it, you'll know what I'm talking about. Write the following in matrix form and augmented form. Bear with me and write this down. I know it seems very trivial, but you want to make sure you know how to do it. Because I literally had students mess up with this first step in the final exam last semester. And they were supposed to be solving like a 4x3 system, but they wrote it as a 3x3 system. And they said, oh, I can take a determinant. They do all sorts of stuff that was completely illegal because none of that applied. So let's make sure that we can actually write this down and we won't make such a mistake. One, A. Okay, matrix form. What would it look like? Matrices like that. Tell me what's written here.
237, the top.
237 in the top row.
The next row is 0, 0, negative 1.
1, 0.
Oh, 1, 0, yeah.
1, 0, negative 1.
3, 1,
3, 1, negative 3. Notice that I put a 0 if a variable does not appear, because I would assume that there's a 0 times y here. It needs to have the placeholder. That's what messed up the student, by the way. The variable was missing and they just ignored the fact that there were 4 variables and they just assumed there were 3. What would go here?
X, Y, Z.
X, Y, Z, go in here. Right, so notice that if you take this times that, you get the first equation, this times that, you get the second equation, this times that, you get the third equation. And here?
5, 2, 1.
5, 2, 1. So this here is your A, that here is your X, and that here is your B. Right? And we'll use that notation in theorems in the future, so that's why I'm getting used to that. How would you write this in augmented form?
each.
In one big matrix, okay, then what?
You append
2, 3, 7, 5. 1, 0, minus 1, 2. 3, 1, negative 3, 1. And a bar.
You write the bar here to show that that's where the equal sign appears in the system. And that's it. But you have to, of course, get that right before you can do anything else. 2, 8. So we know it has to look like this. Okay, what goes in here?
all ones for the first one.
How many?
4.
There are 4 ones. 1, 2, 3, 4.
0, 2, 0, negative 1 for the second row. 3, 0, negative 2, 7 for the third.
Here?
It's a column vector x1, x2, x3, x4. And then column vector 1, 0, 7.
That's called the matrix form. And notice this is a 3x4 system, right? And sometimes the size of the system is going to be able to tell you a lot. When we get later on, we'll prove a lot of theorems about what the size of the system can tell you and what possibilities there are. Of course, in augmented form, essentially you just want to ignore this and stitch these two together. You say you've augmented them when you do that. So it's 1, 1, 1, 1, 1, 0, 2, 0, minus 1, 0, and 3, 0, minus 2, 7, 7. These were brittle from the beginning. Now we're going to take a stroll down memory lane. I'm going to remind you how to solve a system of equations back in the algebra and pre-calculus methods. And I'm going to use that to illustrate some of the things we're going to want to be able to do with these matrices. So the important thing is that you want to realize that this matrix represents that system. It stands to reason whatever manipulation you can do with a system, you should be able to technically do it with this matrix. Right? So I just want to remind you of the manipulations that are legal that we can do, and otherwise it's illegal to do them. So that should be, that's what we're going to do. And I'm going to take preference to one method, the elimination method from algebra class. You would have learned 2 main methods, elimination and substitution. We're going to give preference to the elimination method. It's going to be the one that we're going to use most often. There will be room for substitution, but that usually happens towards the end if you want to apply it. Let me do this one. Now, first we're going to do this. I'm going to do it somewhat in an inefficient way, but there's a point to doing it that way. Normally you would even do it a lot shorter, but let's actually do that. First of all, let's say I want to solve for x. So I'm going to give the x precedence, I'm going to move it up. I can do that, right? Given 2 equations, it doesn't matter what order I write them, it's not going to change it. So I just swap the equations, mostly for aesthetic reasons. Okay, let's move on. What else do we want to do? Let's say I want to actually solve for the x. How would you use the elimination method? What would you do?
multiply the second equation by 2 and add.
Like, the top end.
I want to solve for the x, which means I want to eliminate the y, which means I want to kill the y's, which means I need to make them the same but opposite signs, right? That was the idea. So what would I do here? So I have the first equation, and then what I'm going to do here is I'm going to take the second equation and multiply it by 2. This allows me to have the same answer here, which allows me to now, what can I do? I can add them, right? So when I add them, what do I get? I get 7x
Equals 21.
plus 0y
Oh, yeah.
equals 21, right? Now that is going to be my new first row. Okay. Let me put back the second row. I'm just going to keep writing it here. Okay. Now if I wanted to solve for x here, what could I do? Right, so normally you wouldn't recopy this, but I wanted you to keep the two equations in mind the whole time. How do you solve for x here? You can divide by 7, right? So here what I did was I took equation 1 and added it to equation 2 times 2. And so what I'm going to do in the next step to solve for x, I can divide by 7. And so that would give me what? This should be 21, right?
Yeah.
That would give me 3. So I took the top equation and I divided by 7. Or one way you can also think of this is that I multiply by 1/7. Right? That allows me to solve for x essentially, right? Because now I have x equals 3, right? Which is pretty nice. I still have this guy though. Now at this point what you would have done back in algebra class is you would just substitute x equals 3 here and then solve for the y. But let's actually continue. I want to do the same thing that we did for x, let's do it for the y. Let's actually continue here. Okay? But this step here is important because realize that you could finish it off using a substitution if you wanted to. This step is going to be an important position here. But let's actually just continue and do the same thing. Right? So now I want to solve for the y. I can't do it from the first equation because the coefficient is 0, so I have to somehow manipulate the second equation, which means I'm going to want to eliminate the x. How can I accomplish that?
Multiply by -3.
I can multiply the top by -3. That's still going to be a 0y. That's going to be a -9.
So 1/3, then -1/3 on the bottom.
Coming in. So I took equation 1, multiplied by -3, took the first equation. And now what can I do? Now I can add them. And what's going to happen here? So this was this, I have 0 x's. If I add these two, I have -y. And if I add these two, I get what? -2. I already know a nice form for this equation. Now if I want to solve for y, what can I do here? Because here I know about -y. What would I do here? Just multiply by a -1, okay? So I have x plus 0y equals 3, and what I can do here is I would have 0x plus y equals 2. What I did here was took equation 2 and multiplied by -1. Now could you tell me what the solution is? Right? So if I look for the vector xy that will solve this equation, what would the answer be? Well, from the top you can just read it, right? Because this is just 0y, so it's not going to matter. So I can see right away that my answer is 3. And the bottom one, that's 0x, that guy doesn't matter. I can see right away that my y is 2. Which means this is a very nice form to have the equation in. Right? This form was nice. I could get to the answer using substitution. That form is even nicer because I didn't have to substitute anything. I get here, I can just look at it and know what the answer is. This illustrates to you the kind of things that we can do to a system of equations to find the answer without actually changing the answer. Notice some of the things that we could do here. Swapping equations made no difference. What I could do is I could multiply any equation I want by a non-zero number, right? If I multiply through by 0, I would literally kill all the information. I can't do anything, right? Multiply both sides by 0, 0 equals 0, whoop-de-doo, doesn't help, right? But multiplying by a non-zero number can help me to manipulate it into a nicer form where I can eliminate things. You'll notice that I did that several times. There was another kind of thing we did. There was a time where we multiplied an equation by a scalar and added it to another equation, right? That's another kind of operation that is perfectly legal to do according to the rules of algebra. It stands to reason we could do the same things, operations, on, let's say, the augmented system, right? 1, 2, 7, 3 minus 1, 7. Now, what would that have looked like? I'm going to erase this here. And I can say, since the rows represent equations. So let's actually do that. So I'm going to rewrite this thing. This is how you probably would have done it. A little bit less efficient than you would have done it back in algebra class, but it's to illustrate the point. So the first step, we would have augmented the system. We would have written that as, I believe it was the other way around, right? I had 3x on top. This would be the augmented form of the system. Right? So this is my row 1 and my row 2. In the first step, what did we do? Is we just did nothing other than swap the two rows. Right? We swapped the two equations in the beginning, didn't change the answer, so I could later just put row 2 here, put row 1 here. I swapped the rows in the matrix. Then what did we do? I believe the next thing we did is we wanted to eliminate the y, right? So what we did was we took this guy, so I took row 2 from the previous stage, and I multiplied it by 2. And then in the next step, what I did was I added it. I took row 1 and added it to the new row 2. So now that when we add these, I would get 7, I would get 0, I would get 21. Put this back. What was the next thing we did? Well, we decided to get into a nice form to solve for the x. Because I understand that the 7 really is the coefficient of x. Everyone in the first column is going to be a coefficient of x. I decided to divide the first row by 7. This gave me 1, 0, 3. So I took row 1 and I divided by 7, or I multiplied it by 1 over 7. And notice that this here was a very nice form to have a row in, right? Because that's telling me the coefficient of x is 1, the coefficient of y is 0, and this is the equal sign, and that's a 3, right? So having a 1 and a 0 everywhere else in the row is kind of a nice thing to have, okay? So we could have stopped there and solved the system, but we continued. And we wanted to do the same thing with the x. So this guy allows us to find x easily. Can find x easily. But we continued, because we want to do the same thing with the y. So what we did here we could multiply this by, we did -3. So I took row 1 from the previous step, multiplied by -3. And then what I did was I changed row 2 by now adding the 2 rows. Add these two, I get 0. Add those two, I got -1. Add those two, I got -2. And ultimately, I could finish that step by taking the second row and multiplying by -1. That would give me 0, 1, 2. This will give me 1, 0, 3. And you'll notice that now this column here looks just like our answer vector here. Notice that over here, this guy looks like the identity, but it's a very efficient form, right? Notice that once you have this array of numbers, you can literally just look at it and know what the solution to the system is, right? The coefficient, the number in here is the coefficient of the x value. Clearly from row 1, my x is 3. Coefficient here is the number of the y values. Clearly from row 2, my y is equal to 2. So right here, I can say my xy is equal to 3, 2. So we literally just stopped moving the variables around and just decided to augment the system and just manipulate this array of numbers, right? And how we manipulated it was inspired by what we could do with an equation. Anything we could do with an equation, we can do with a row in this augmented form. So we're going to end now with me saying what the legal moves are. Given an augmented matrix, meaning that you have a matrix that you understand represents a system of equations. There are 3 types of things we can do, right? We want to make these as elementary and as basic as possible. There is something called a type 1 row operation. And that is to swap 2 rows in the matrix. So given an augmented matrix that we know represents a system, I can do a bunch of things on the rows of that matrix that will not change the solution of that system. In fact, I can use them to change the matrix into a nicer form where the solution is obvious to me, right? One of them is I can swap 2 rows, which is what I did here. This is called a type 1 row operation. There's another thing we can do, which is called a type 2 row operation. And this is how your textbook labels them. So that's called a type 1. I can swap the rows of a matrix that represents a system, and it won't change the solution of the system, because that's like just writing a system of equations in a different order. It's not going to change the answers. This is what we call a type 2 row operation. And this is multiplying a row by a non-zero constant. I can multiply both sides of an equation by any non-zero number and not change the solutions of that equation. Therefore, I can do that to a row in a matrix without changing the solution of the system it represents. This is called a type 2 row operation. There's a type 3 row operation. Which is a little bit more technical. This was the process where we actually did the elimination. I multiplied something by a constant and added it to another row to kill one of the variables, right? It's going to be phrased in a very specific way. It's not that you have to do it that way in practice, but there are certain theoretical things that will work out when we phrase it this particular way. So you should remember the particular way that it's done and phrased. This is replacing a row by itself plus a multiple of another row. This is called a type 3 row operation. This was what allowed us to finally do the elimination and kill one variable and leave the other one alive. But we first want the operation to be a very elementary thing that's, for one, you can do, and for another thing, it's easy to program in a computer. But also, we phrase it in this particular way. You're changing a row. The row that you're changing, you don't do anything to that row. You multiply another row and add it to that one. Technically, you don't have to do that. But if you do something similar to this, anything you do should be a combination of one of these three types of things, right? This one, in this phrasing, it's very important for theoretical considerations, but if you can multiply the row that you want to change by something else, it's going to be fun. But you'd actually be doing a type 2 and then followed by a type 3. You're doing two at once. But these are the elementary row operations. Literally anything else you do to a matrix that represents a system that is not one of these or a combination of one of these, you've done something illegal. Okay? These are the only three things you can do on an augmented matrix and not change the solution to the system. Did you have a question? Oh, okay. Are there any questions so far? Using row operations transform a matrix into a convenient form, i.e. the kind of form where I could see the answers. Is called elimination, or row reduction. That's the name of the process, right? So if I started with some sort of augmented matrix that represents a system, I did a bunch of row operations to get it to a nicer form, we would say I have just performed row reduction, or I have just performed elimination. And there are classifications of eliminations that you can have. There's Gaussian elimination and guass-jordan elimination, but that's in the next chapter. And that's the end of 1.1. Any questions? All right, so the main takeaway of 1.1 is given a system of equations, I can write it down using matrices. And then using these things called row operations, I can get that augmented matrix into a very convenient form where I can talk about the solutions in a more obvious, straightforward, in-your-face way. Right? I can see the solutions right away by looking at the final version of the matrix. So in 1.2, I think is the next step, we're going to define this guy. What is a convenient form? What are the convenient forms that we want to get to? It turns out that there are two of them. So I'm going to tell you what these forms are. We're going to describe them. Make sure you know how to identify them. And then I'll talk a little bit about an algorithmic way of achieving them. Right? But at any given point, you should know that to get here, you need to be doing one of these three types of operations, or some sort of combination of them. Otherwise, you're doing something illegal. So that brings us to 1.2. Gaussian elimination. And guass-jordan elimination. It's named after two mathematicians. Gauss is the mathematician. I mentioned that story about adding the numbers from 1 to 1,000 when he was 4 years old. Gauss was a genius, very prolific mathematician. And there are many things in math and physics that has his name attached to it, more than you realize. It's kind of like Euler. They're literally almost everywhere. So we're going to talk about these two things. When doing a row reduction, two forms are particularly convenient. These are called the following. One, it's called row echelon form. Two, this is called reduced row echelon form. I will abbreviate this by REF. So from this point to the end of the semester, anytime you see me write down REF, I'm talking about a row echelon form. I will abbreviate this by RREF. When it comes to solving a system, either form is okay. However, the row echelon form, it turns out it's not unique. While the reducer echelon form is a unique form, like any system that you bring to reducer echelon form, no matter what steps you take in what order, everyone would end up with the exact same looking answer. Whereas if this one, you might have different looking answers, but they're all equivalent, right? If you actually went through with the substitution, you'd eventually get the correct answer. So there are times when I might request this way, but that's just because it's easier to grade if I know everyone should get to this point as opposed to that way. But in general, there's not, one isn't inherently better than the other. For most things that we'll be doing, either form will be convenient, but there are two main forms. Okay? So let's talk about the row echelon form. And this is just something you have to know. You have to know what this form is because every now and then you want to achieve it, right? So you have to know what these forms look like. And they're basically just forms that makes it easy to talk about the solution to your system. So here's the row echelon form. There's a list of criteria that you must achieve. 1. Any rows of all zeros are at the bottom of the matrix. Alright, so if you have a row of zeros that's not at the bottom, you can just swap rows until it reaches to the bottom. Right, so you can just make sure you move all rows of zeros to the bottom of the matrix. 2. Right, and that's because of a back substitution rule. You want to be algorithmic in how you're back substituting, and it makes sense to have all the zeros at the bottom so you can back substitute up the stairs in all the other rows. 2. The first non-zero number in a row, if any, should be a 1, the number 1. This is called a pivot or leading 1. I'm going to do a slight caveat here. I believe in your online homework system it doesn't particularly care about this particular criteria. Right. So if you're trying to satisfy this criteria and you're plugging into your online homework and it's not working, just be aware that you can just write it such that everyone's an integer and the online system will get it. But for us, it is a criteria, right? It's a very standard thing to do. Make sure that the first non-zero number in a row is 1. Okay? So if you have any rows of zeros, move them all to the bottom. Any row that has a non-zero number, the first guy you encounter in that row when reading from left to right should be a 1. We call this a pivot or a leading 1. 3. All pivots obviously except for the top should be to the right of pivots in rows above them. Right? So you'll notice that we had that last nice version here. I believe this was 32. Right. Notice that in our language, the last step we had, these two would be called pivots. Notice that the pivot in the second row is to the right of the pivot in the first row. Right? It doesn't have to be immediately to the right, it doesn't have to be in the very next column, but it has to be in some column that's to the right of the pivot in rows that are higher. Right? So you should have your pivots kind of cascading along the diagonal or some close approximation to the diagonal. Right? If you had the thing in like this form, then this is wrong, right? Because here I have a pivot in the second row, but it's to the left of the pivot in the first row, right? So the pivots should be to the right of any pivots that are above them. This is one of the criteria. I think that's enough. You can just double check here that and that's it. If these 4 criteria are fulfilled, we say the matrix is in row echelon form. It's one of the convenient forms that might require some back substitution to get to the answer, but it's a very convenient form to start with. This is called the row echelon form. It is something you should know about. process, I'll tell you the name here. The process of using So if you use row operations or row reduction to put a matrix in row echelon form, you say you performed Gaussian elimination. So using row operations to put a matrix in row echelon form is called Gaussian elimination. That's a part of the title of the chapter. And this is something less to understand and more to just know, right? This is just a form that we find convenient, right? So, and this is the criteria that defines them. It's just a form you should know because every now and then you'll have to put a matrix in this form, so you should know what it looks like. It's just a thing to know. We know now. Let's talk about another convenient form, the reduced or echelon form. So it's like going to row echelon form, but you take it a step further, right? It's kind of like when we got to a point in our system where I put the star. It was pretty convenient to be there, but we wanted to go get even more convenient. That's what row echelon, reduced or echelon form is about, getting even as convenient as possible, right? And where there's no extraneous information, everything is as tight as possible, and it's easiest to find the solution in this form. So one, is to get to the row echelon form with one additional criteria. Where's the criterion? 2. Kill everyone else in the column that has a pivot. Everyone else should be a 0. In particular, not only do we want zeros below every pivot, but we also want zeros above every pivot, except for the one that's in the top row. There are zeros everywhere else in the column. So once you're in row echelon form and you tighten things up to fulfill that additional criteria, you say you've reduced it. You put it in reduced row echelon form. And it turns out that's actually a unique form. And this extra step if you perform it, you say you're performing Gauss-Jordan elimination. The power of two mathematicians, not just one. More power! It's like you tag team and you bring in that extra step. So now it's like as efficient as possible. You can't get in a better form than this as far as solving a solution is concerned. Fact. REF is not unique in general. But RREF is. Right? Every matrix has exactly one reduced row echelon form, but it might have multiple row echelon forms. And those are the nice forms. Now, I do want to emphasize, you would notice that none of the criteria says anything about the actual order of your row operations or what you should do first or second, because honestly, it doesn't matter. It means I could give you a problem to reduce a matrix, and you could probably do it in 3 steps, but it might also take you 20 steps if you're not very efficient, right? So there is a certain algorithm and way you'd want to do things to be more efficient, and I'll talk about that in a bit. But there is no unique way to get to one of these forms, right? Someone can just randomly decide to switch around rows for no reason and take up like 100 steps doing that before they actually start doing anything meaningful, and nothing would be wrong with that, but why would you do that, right? You'd actually do things to be a lot more efficient, and I'll tell you a little bit about how you'd want to do that by hand, because we do expect you in this class to be able to do this by hand. Before that though, I want to make sure you guys can actually recognize when one of these forms are here, right? Because that's half the battle, recognizing what it should look like, and then you'll know how to get there when you have the opportunity. Is everyone done writing? So I'm going to write down a bunch of matrices on the board. You are going to tell me if they're in row echelon form or reduced row echelon form or neither. And if, of course, if neither, you can tell me why. And just to make sure you know how to look at these matrices. REF or REF or neither. That is the question. Here are the options. That matrix. That matrix. That matrix. Space icon, so identify them. Should have colored chalk. Oftentimes I want colored chalk, but they're hard to erase, so it sucks. Colored chalk sucks. Okay.
Hurry up.
So row echelon form. Why is it not reduced?
Because there's a 2.
The 2 is the fact that it's not reduced. That 2 had to be a 0. If that 2 were a 0, it would be reduced, but as written, it's in row echelon form.
Row echelon form?
Reduce row echelon.
This is actually reduced row echelon. How do we know? Let's go through the criteria. All rows have zeros at the bottom. First non-zero number in each row is a 1. 1s occur to the right of 1s above it. And literally below them, they're all zeros in the column, but also above, they're all zeros in the column. So this is actually reduced row echelon form. Neither. Why?
2 1s in the same column.
This guy, right? Both of these are pivots, but this guy in the lower row is not to the right of the one in the upper row.
Row echelon form?
It's row echelon form. Why isn't it reduced row echelon form?
2.
Again, because of this 2. 2 is always messing up.
Neither. The 2.
Again, the 2. That needs to be a 1 for our purposes. This is reduced row echelon form.
Neither.
Why not?
Because the zeros are at the bottom.
Here I have a row of zeros, smack dab in the middle, so it's neither. Fails criteria 1.
Row echelon form.
This is row echelon form. Right? 0 rows at the bottom. First non-zero number in each row is a 1. All 1s appear to the right of the ones that are above it. All elements below the pivots are zeros. However, all elements above the pivots are not 0. So it fails the last criteria of the reduced row echelon form. So that is row echelon form. Yeah.
What would be the point of having a row of all zeros?
Hmm?
Like, why? When would that occur? Like, isn't that just saying nothing?
Well, in context, you would reduce something to be like this. So it's like situations like this show up when you're considering a bunch of equations, but one happens to be a multiple of the other. Right? You'll have meaning in terms in context. So remember, if like I have an equation that this is like 1, 2, 3, and this is 2, 4, 6, then to put that in reduced row echelon form, right? I have this, but then I could get a bunch of zeros here. Right? Because I'd want to make this guy a 0, but then if I multiply this by 2 and subtract that, it literally kills everyone.
You wouldn't say it's just one equation in there.
No, you wouldn't ignore that row. Again, because dimensions are important, right? Because you'd be eliminating some variables, right? So if you look at it this way, right? If this represents a linear transformation, this means that the input space is 2-dimensional. If you look at that, your input space is now 1-dimensional. You've completely changed the situation. So there are times when 0 rows can show up. You cannot ignore them, but to be in a nice form, move them to the bottom. Right? There are dimensional concerns for not ignoring them when they do show up. Okay. So if all you ever need this for is for solving, when it comes down to solving a system, you essentially ignore this row when you're writing down the solution, but in a larger context, you can't ignore them. hopefully now we know what the reducer echelon form would look like. Let's actually put some things into reducer echelon form and find some solutions. So we're just going to, what we're going to do is I'm just going to solve some systems with you guys, and we're going to do it by converting them to augmented matrices and doing reduction. And while I'm doing that, I'll talk about efficient ways to do that to make sure you're not wasting steps. Because there are times when I'm doing I give a quiz and I do the solution, and it's like, oh, I did something in like 3 steps. I'm like, how did you do that? And people like go down and no other column turn to the back of the page, and they're doing like 20 steps to get to the same. Like, why are you doing all this? I don't know what I'm doing. They're just randomly just doing row operations and hoping that it turns out okay. That's not how you want to approach it. There's an end goal. There's an algorithm you want to have in mind. So I'll talk a little bit about. So again, there's no unique way to do this, but it helps for you to have some sort of process that you're going through, some sort of goals that you're trying to achieve. So let's actually just get to that. And we'll do this all in one by solving some equations. Elimination. Use row reduction. I don't know if we'll finish all 3 of these in time, but let me write them down and we can continue next time if not. We can actually kill 3 birds with 1 stone by going through these examples. So I'll show you how to solve the system using matrices and row reduction. While doing that, I'll tell you some of the algorithmic cues that you'd want to follow, and at the same time, by finding the solutions, I'm actually going to show to you all the possibilities when it comes to solutions for a linear system. It turns out there are only 3. Right? No matter what the size of your system, 1 of 3 possibilities will happen. And these examples are going to illustrate them, and then we're going to prove that these are the only possible cases. Okay, so proof is coming up soon. By next class, we're going to start doing proofs. It's not going to be completely computational. So here's my first example. In the right, I think that was 3x1 plus x3 equals -1. So double check that. This thing's not done. It's 4 x1 plus. Just changing one little number here can make this thing into a nightmare. Okay. Second example we're going to do and what we don't finish today, you can even try at home because the process is going to be essentially the same except maybe for the last step, and maybe you guys can discover on your own what we'll do in next class. This is a -2. -2, 3, 1, sure, x1 minus 2x2 plus 3x3, minus x1 plus x2 minus 2x3, 2x1 minus x2 plus 3x3. And the third example we're going to do. check that. So minus 2x2 plus 2x3 equals minus 2 minus x1 plus x2 minus 2x3 plus 1 minus x2 plus 2x3 plus 1 plus Okay. We're going to do these. We're going to solve these three systems. Okay, use row reduction. So we're going to solve 1, and so I'm going to tell you the steps here while we're doing it. Step 1, augment the system. So what would that look like here? First row is what?
Negative
2,
2,
negative 1, negative 1, 4.
Second row.
1, 2, 3, 13. 3, 0, 1, negative 1.
Now here's the first thing you're going to want to do. Step 2. Immediately establish the top pivot. And in most cases, in one fell swoop, you'll immediately be able to kill all the numbers below it. If you take several steps to kill all the numbers below the first pivot, you're wasting time. You can usually do it right away. So let's see what that would do. The top pivot we know has to be the topmost and in the farthest left corner, right? Which means this position, I want to immediately make a pivot, right? So you want to really think about the easiest way to accomplish this, right? So I want that to be a 1. What's the easiest way to get a 1 there?
Swap rows.
Swap rows, right? That would be your first step. So I'm literally going to swap and put row 2 in the top. Now right away, I want zeros everywhere else here. Okay? Now how would I get a 0 everywhere else there? Right? Right, so I need to do 2 operations that are going to give me zeros in the first step.
2 type 3s.
Okay, well, how? Give me a couple.
Multiply the first row by 2 and add it to what is now the second row.
Okay, multiply this. I like to use labels. Like you'll see me label things here. How I label them is the row position refers to the previous step.
Okay.
So when I write R2 here, I'm referring to R2 from the previous step. That's just how I do it. So here, and at this step, if you're looking at things, you're talking about row 1, row 2, row 3. So tell me the first thing you do. You can take 2 times this and add it to that,
Yes.
right? So I know I immediately want a 0. One way to do that is to take 2 times row 2 and add it to row 1, right? So I'm doing a type 1 operation, and the goal is to get a 0 here, right? That's my algorithm Q, right? Establish the first pivot, the highest one, immediately kill everything below it, right? So if I take 2 times this plus that, that's 0. 2 times this plus that is what?
5.
2 times this plus that. 2 times this plus that.
30.
That's my new second one. I want to do something to get a 0 here. Now I need to use 2 other rows to do that, right? So I use row 1 and 2 to get that second row. So maybe use row 1 and 3 to get the other one, because that'll be easier. What I can do is take 3 times this and minus that, right? So that's my idea. I'm going to take 3 times row 2 and subtract row 3, right? Which technically I'm doing 2 row operations at once, right? I'm doing a type 2 here and then I'm doing a type 3 row, whatever, right? I'm doing 2 legal things at once, but the goal here is to do efficiency. I'm not doing elementary operations, I'm just doing row operations. But I don't want to take like 20 steps to do something that I could take 3 steps to do, right? Because remember, it's only arithmetic that we're doing. It's nothing complicated, but when you're doing it a lot of times, errors will creep in. So you want to minimize the amount of time you spend doing the arithmetic, right? Because you're just giving the longer you take, the more opportunity there is for you to mess up on a number, drop a sign, multiply something wrong. So you really want to be efficient, okay? So you immediately establish the first pivot and right away kill everyone below and using illegal row operations. So what I'm going to do here is the quickest way to get a 0 using these 2 is I'd say multiply this by 3 and subtract that. So 3 times this minus that is 0. 3 times this minus that, 6. 3 times this minus that, 8. 3 times this minus that. Right, so if you're doing a row reduction and your first steps looks like that, you're pretty efficient. Right? If either one of these guys are not 0, you're wasting a step. You're creating more opportunity for mistakes and you're going to take a longer time to get to the answer than you should. So these are the 2 cues you should be thinking. Augment is step 1, immediately establish the first pivot, kill everybody below him, right? And you kind of rinse and repeat at this point with the next pivot, right? Establish the next pivot in the immediately lower row. I know the pivot has to be immediately in the lowest row because in the row echelon form, any rows of zeros would be pushed all the way to the bottom. So if there are more than 1 pivots, they will be in successive rows. Establish the pivot in the next row. Kill everyone below him. So that's my first pivot. My second pivot should end up in this position, right? Because that sort of makes sense. Okay? I wouldn't jump over here where there's a 6 over here. That's going to ignore the second part of my criteria. So my next pivot should end up here. So that's the guy I want to now make into a pivot. What's the quickest way to make that into a pivot? Divide by 5. Notice that everyone in that row is divisible by 5. I'll make a comment about fractions later. I could just make it now. You don't want to get fractions too early in the game. You don't want to end up in a situation where you're adding a bunch of fractions. That just makes things harder, right? If you get fractions, wait until the very last step. There might be times where I wait to make this a 1 until the last step because I know I can eventually get that 1, but I'm not going to force it unless turning it into a 1 doesn't create any other fraction. In this case though, dividing through by 5, everyone is a multiple of 5. It won't create any fractions. So that's how I'm going to establish the next pivot. 1, 2, 3. Right, and this is just my cue. Notice I'm leaving the first row alone. It's not a concern of mine anymore. He already has his pivot established. I'm moving now to establish the next pivot. Quickest way to do that is to just divide by 5. So I'm going to take row 2, divide by 5. Now that's the next pivot, which means in my next step, I want a 0 here. Right? Let's not waste any time. Okay? How can I get a 0 there?
Multiply row 2 by 6, subtract row 3.
Yeah, multiply this by 6, and then subtract that. Or it probably would be nicer the other way because of no negatives, right?
I have a quick question though.
Yes.
Sorry, but you could also arbitrarily multiply the top row by 3. Like, I'm saying there's different ways to do this, right? Just to be clear, or no? Like, could I multiply the top row by 3 at this point?
No.
Okay.
Why? You could, wouldn't be illegal. Why wouldn't you want to do that though?
You start with the 3.
You mess with the first pivot.
You mess with the first one. See, if I multiply this by 3 to add to that and kill it, I now have a non-zero number adding to the 0. I would have gotten rid of that 0 I already took the effort of putting there in the first place. So I wouldn't want to mess with these 2 rows because that's going to kill this 0, and I need the 0 there. So technically it's not wrong, but it's not very efficient. You'll be undoing some of the work here. So once I have these 2 0, once I have a 0 in the first column, I don't want to mess with any row that doesn't have a 0 in the first column, because that's going to get rid of the 0.
Question. So back to what we were saying there. If you were going to do that, would you be referencing something of your current matrix as opposed to the previous one? Like,
Yeah,
would you have to
I
introduce
mean-
something new.
I'd want to be able to say, just multiply this by 6 and subtract that, or
Okay.
vice versa. So what I would say here
Would
is
you call it like a prime?
take, no, I don't, because when you're looking at the numbers, you can easily see, it's actually write down this part here is going to be the hardest thing. But essentially what I'm going to do is I'm going to take row 3, which is this guy, and subtract 6 times the row I just created. So what I can do is just subtract 6 times, I know the row I just created was this guy. So to be pedantic, you should technically write that down. But in practice, it's going to be easier for me to see. I'm just going to take this minus 6 times that, 0. This minus 6 times that. This minus 6 times that, so it's 40 minus 36. Right? So if you take 2 steps, you should be establishing 2 pivots, in other words. Right? The pivots are going to be the most important guys. Everything pivots on them. Right? So you want to establish them as early as possible and kill everyone below them as possible. You work on killing things above them after all pivots have been established. So if you want to go all the way to reducer echelon form, by hand, algorithmically, the best way I've found is to just first focus on killing everyone below the pivots, then afterwards worry about killing people above the pivots. So for now, I'm just establishing all my pivots. So I'm going to want to get the last pivot, which is going to be in that position, obviously. There's no one below that to kill, so I'm just going to worry about, can I get a 1 here without creating fractions? Sure, it's easy. I can just divide by 4, divide by 2. So, kind of step 4. Rinse and repeat. Establish all pivots before moving on to the next. So far I have 1, 2, 3, 13, 0, 1, 1, 6, 0, 0, 1, 2. I just took row 3 and divided by 2. Now by the way, this is REF. Right? I just got to REF by taking 1, 2, 3 steps. Right? Could have taken me more. But it's a pretty efficient way. If you establish pivots right away and get to kill all zeros below them, you get to REF in pretty much as quick as possible. As quick as humanly possible. Okay, so that's where we are. So this, by the way, is REF. And by the way, this is enough to solve the system. Let's go a little bit further though. Let's take it to RREF. So step 4. Kill numbers above pivots. Keeping in mind that you need to not mess with any of the zeros that you just worked so hard to create. So let's establish this guy again. Start pivot in second row. It's easier to just eliminate from the bottom down. So I want to make this 2 into a 0. How can I do that?
R2 minus R1.
I want to replace this with what?
R1 minus.
R1 minus 2 R2, right? So this minus 2 times that, 1. This minus 2 times that, 0. This minus 2 times that, 1. This minus 2 times that, 1. So that turns this into a 0. I could in the same breath get this into a 0, right? How would I do that? Just take row 2 minus row 3. This minus that, 0. This minus that, 1. This minus that, 0. This minus that, 4. And this guy is just recopied for now. Now the only problem is this guy here. So I can just do one more step to get that done. And just take row 1 minus row 3. This minus that, 1, this minus that, 0, this minus that, 0, this minus that, minus 1, 0, 1, 0, 4, 0, 0, 1, 2. Notice that this now is in reduced row echelon form. Can you tell me the answer to this system? Do we use x1, x2? x1, x2, x3 equals
Negative 1, 4, 2.
negative 1, 4, 2. Yes?
Just to be clarified, the first equation was x1 minus 2x2 plus 3x2 is equal to negative 2?
The first equation?
Yeah.
No. It was minus 2x1 plus x2 minus x3 equals 4. Let me just take a minute and show you, just quickly. If I didn't require you to go all the way to reducer echelon form, you could actually get to the solution with a little bit of work from here, which we call back substitution. So I just want you to show you that. And you guys can try the other two later. From the REF form, we can use back substitution. And back substitution works from the bottom row up. Of course, unless it's a row of 0. Bottom row up. So for example, from R3, I would start in row 3. In row 3, clearly I see that x3 is 2. So I move up to row 2. Right? Clearly now I see that x2 plus x3 is 6. But this allows me to plug in a 2 here. So I get x2 plus 2 equals 6. This means that my x2 is equal to 4. Moving up. Right? And because we cascaded the pivots in this way, that will work. We can start from the bottom row and work our way up and find all the guys if we chose to stop at row echelon form. So in row 1, that tells me that x1 plus 2x2, and having it in this form ensures that we find all the variables needed for the next step in the order that we need them. 3x3 equals 3. I can actually plug in my x2 equals 4, which would make that 8. I can plug in my x3 equals 2, which would make that 6. Would that be 6? What would you get here? You'll end up with minus. So you could actually get to the solution there, and then you write this down. So you can take it all the way to reduced echelon form and get to the answer right away without doing any work. But if you're in row echelon form, you can easily do this back substitution, start from the bottom row, move up, and you can find everyone that way as well. So it turns out that this system has a unique solution. There's only one vector that solves it. This is actually one scenario that you can end up with a solution to a system of linear equations. So you're given a linear system of equations. One possibility is you have a unique solution. Only one vector will solve it. We'll look at the other possibilities next time. See you guys tomorrow.
Yeah, I think you meant to write like 1 there. 13? It's not 3.
Oh, sorry, yeah.